All right, guys, let's get into lesson 9.2. So, we're going to talk about power series because they're super powerful and we can do a lot of cool stuff with power series, okay? A series with terms like 1, x squared, x to the third, x to the n is called a power series. This in particular is a geometric power series. Now, it's really important. Let's review from last time. Geometric series is when you multiply by something every time. You guys can see it here. Every time I'm multiplying by x, okay? The other thing I want you to remember from last time that was specifically with geometric series, the sum of all the terms was a1, the first term, over 1 minus r. That's going to be important in this lesson, okay? Now, we also talked about geometric series can only converge when r, which is what you're multiplying by, the absolute value is less than 1. So it must be true about x. X is r in this case. So the absolute value of x is less than 1. And remember a lot of times that we can write that as -1 is less than x is less than 1. So that's just kind of a little bit of background information. Okay? Now, if you remember, all right, so we're multiplying by x. If we sum all of this up, the sum of this is going to be a1, the first term, over 1 minus r. All right, and that's the same thing as, we can go here 0 to infinity, and we can call x the n. That way my first term is 1. Okay, so those are two things that we want to kind of remember. Okay, so we have those two things here. We have this geometric power series here, and that can be written as a summation of all those terms. Okay, so now we're going to find a power series for each of the following functions. All right, we're going to show the first 4 terms and the general term. We're going to write it in sigma notation, and we're going to give something called the interval of convergence, which I haven't showed you yet, but I'll show you in a minute and it'll make sense, okay? Okay, now what you have to do is kind of make it match the pattern. Remember, the pattern is a1 over 1 minus r. This is important, the fact that that's minus. So in order for like this first one to match the pattern, okay, a1 is 1 and r is actually negative x, because that way when I write this as 1 over 1 minus negative x, it becomes 1 over 1 plus x. But it's got to match the pattern, and I need to have a minus in there, okay? Okay, so now that we've determined what that is, that means that my first term is 1, and that every time I'm going to multiply by negative x. So 1 times negative x is negative x, times negative x is positive x squared, times negative x is negative to the third. That's 4 terms. Okay? And you guys, this is x to the n, but it's also alternating. Now, I want to tell you what alternating means. Alternating is where, we put x to the n, is where in front of it we put -1 to the n. Now, the reason -1 to the n does alternating is because it's like, let me write out a few. A negative to the first is negative, a negative to the second is positive, a negative to the third is negative, a negative to the fourth is positive. So it makes it alternate. And the only thing you have to be careful about is where does it start? And do you have to put n or n plus 1 or n minus 1? You can put one of those. N plus 1 and minus 1 are the same thing. It just means, am I starting with a positive or a negative? So look, in this case, if it's x to the n, that's like the 0th term because it wants to be x to the 0 and -1 to the 0. So I'm good with that term right there, okay? So that's called my general term. And then I put plus ... because it goes on forever, all right? 4 terms, general term, sigma notation. So I started at 0 on this one. And then you put the nth term in here. Okay? Now you might be thinking, could I just put -x to the n? And you actually can for this. but, you know, it's easy enough to separate the alternating piece. All right. Now, the interval of convergence, what we do is we take the radius and we say we know that absolute value of the radius has to be less than 1. Well, the absolute value of negative x is just x. And instead of saying the absolute value of x is 1, when we write an interval of convergence, we usually write it like this. You can call it the IOC. And the interval of convergence on this one is negative 1 is less than x is less than 1. Okay, cool. My next one to find the all the stuff here. All right, look, that's my A1. And it already has a minus in it, which is good, so that's my R. So what this means is this is a series that starts at 3, and it multiplies by 2x every time. Okay, 3 times 2x is 6x. Times 2x is 12x squared. Times 2x is 24x to the third. All right? And then as a general term, it's going to be 3 to the 2x to the n. Okay? Let's check that. If I start at n equals 0, that works. We have to put plus dot dot dot. I was running out of room. All right, and then to the 1 and to the 2. So I kind of checked that through, and that looks great. And then it's n equals 0 to infinity of that general term. Okay? If you cared that much and you like really wanted to start it at 1, that's fine. Then you just have to put n minus 1. All right? But it's up to you, and you'll kind of see the way that we do this. All right, for this one, the interval of convergence, I know that R, which is 2x, the absolute value of that has to be less than 1. So I'm going to split it out like this. Negative 1 is less than 2x is less than 1. And to solve, I divide everything by 2. So I get negative 1/2 is less than x is less than 1/2. This is my interval of convergence for this power series. Okay, which means that if this power series wants to converge, the x needs to be between negative 1/2 and 1/2. Okay? All right, sweet. Let's look at this last one now. This one's a little bit weird. Very weird, actually. Because remember that we have to get it into A1 over 1 minus R. Okay? And there's like no 1 minus right here, but I have to make it work. So this is A1. Now, how do I make 1 minus R equal 3x? Right? This is what you have to come up with, and it's a little weird. So here's what I'm going to do. I guess we could actually solve. Like, we could solve that. That might make more sense to you guys. So, for example, minus 1. So negative whatever's in the parentheses has to be 3x minus 1. And if I divide by a negative, then what's in the parentheses has to be negative 3x plus 1. So that's like one way to do it. Here's the other way to do it, is you just go, I know I need to cancel the 1 out. So 1 minus 1, that'll cancel out. And then the 3 needs to be positive. So if I make that negative 3x, it becomes positive 3x. Okay? So that's what R is. So if I change this to 1 minus parenthesis 1 minus 3x, okay, that's R. All right, it's a little weird, but we had to put like the 1 in there to get that to work. Okay. Okay, so now let's go ahead and write the first 3 terms. So it starts with 1, and every time I'm multiplying by 1 minus 3x. So then the next time it's 1 minus 3x squared, and then it's 1 minus 3x to the third. That was 3 dots right there. You just can't see that dot. Dot, dot, dot. Okay, and then the general term is 1 minus 3x to the n. Okay? Okay, in sigma notation, n equals 0 to infinity of 1 minus 3x to the n. And my interval of convergence is, okay, 1 minus 3x has to be less than 1. So I'm going to go negative 1 is less than 1 minus 3x is less than 1. Okay, if I'm trying to solve this here, subtract 1 from each, I get, that crosses out, negative 2 is less than 3x, negative 3x is less than 0. And then you guys, when you divide by a negative, do you guys remember this? You have to switch the sign. So it goes 2/3 is bigger than x is bigger than 0. You can leave it like that. I just think it looks a little funny, so I'm going to rewrite it. That's my interval of convergence. So this will converge if x is between 0 and 2/3. Okay? Okay, now we're going to do some stuff with these power series, and it's going to be kind of weird. All right. Using the power series from example 1. So that's the power series from example 1. Make a new power series for f of x squared. So here we go. My new power series would be 1 minus x squared plus x squared squared minus x squared to the third, like that. And just make it look nice, 1 minus x squared plus x to the fourth minus x to the sixth plus dot dot dot. Okay? Oh, and like we can say what these are like this one is the summation of it at least equals, okay, a1 over 1. Now this is alternating again, so we're gonna write, it's like minus, and this time we're plugging in x squared, because this one was 1 over 1 plus x. So now this one is going to be 1 over 1 plus x squared. Okay? Cool. All right. For g, this was the one from example 2. Oh, it started with 3. And it was over 1 minus, I don't need parentheses, 2x. Okay. So now make a new power series for g of square root x. So it's 3 plus 6 square root x plus 12 square root of x squared plus 24 square root of x to the third, right? And this one would be, it would sum up to, I should put an equals right here, 3 over 1 minus 2 square root x, because we're just substituting in the square root x. Don't ask quite yet why we're doing this, we just are. So we want to be able to do some algebraic manipulations to the series that we're making. Okay, so other things that we can do when we start having series is we can find derivatives and integrals, okay? So I know this is going to be like super weird, all right? Just hang with me, okay? Let's go ahead and write out my power series for f of x. So it's 1 plus x squared plus x to the third, like that. And maybe if I want 4 terms of this one, I might go out to 5 terms on this one. I'll show you guys why. Because now, what are the derivatives, okay? Well, what's the derivative of 1? The derivative of 1 is 0. What's the derivative of x? The derivative of x is 1. And then the derivative of x squared is 2x. And then it's 3x squared, and then it's 4x to the third. So I went out at extra term because it like started with 0. But anyway, there's my power series for f prime. Okay? All right. This is J. We want to find the power series for J prime. Now, this is weird. Okay, guys. This is the first time we're going to start seeing factorials inside of like power series. Okay, but let's go ahead and find the derivative. Now, I want you guys to remember a couple of things. All right. I'm kind of like write this down. That's 2 times 1. That's 3 times 2 times 1. That's 4, 3, 2, 1. That's n minus 1, n minus 2 down to 1. Okay? You just need to know that for when we find our derivative. All right. The derivative of 1 is 0. The derivative of x is 1. Now, you guys, when I take the derivative of this, the 2 comes down in front. Constants on the bottom can stay on the bottom for right now, okay? This derivative is 3x squared over 3 factorial. This derivative is 4x to the third over 4 factorial. The general term is n x to the n minus 1 over n factorial. Okay? And if we go ahead and simplify this, right, here's what I get. 1 plus, now right here the 2's will cancel out, so I get x over 1, so I get x, plus, right here the 3's will cancel out, so I get x squared over 2 times 1, which is 2 factorial. Okay? The 3's canceled out on that one. On that one, the 4's will cancel out, so I get x to the third over 3 factorial. On this one, the n's cancel out, so I get x to the n minus 1 over n minus 1 factorial, which, if I went one more term, would be x to the n over n factorial. Okay, now I want you guys to look at this original function. I'm going to erase my work here. Look at this original function and look at this derivative. And what do you notice about the original function and the derivative? Okay, 1 plus x squared over 2 factorial plus x to the third over 3 factorial. And look at this one, 1 plus x squared over 2 factorial plus x to the third over 3 factorial. So what function do we know that has, let's put it like this, what function is its own derivative? Okay, you guys can think of that, right? And that function is e to the x. So we can identify this. Now, this is something that we're going to get into big time in a couple of sections here, okay? But the fact that e to the x can be expanded by this power series right here is actually super, super awesome. All right, some crazy stuff happens. Okay, now we'll get into this more in like a different lesson, but check this out, you guys. So I have e to the x graphed. Now this power series, remember, 1 plus x squared over 2 plus x to the third over 3. Remember the other day when we were doing series to like approximate stuff and I was adding them on in Desmos and adding on each little term and seeing like how approximate we could get, okay? Okay, well check this out. Let's say I just take the first term. Those do not look very much like the same graph. That's not a great approximation. 1 plus x. Okay. That's a little better, especially like if I zoom in. Are those things like pretty close to each other? Kind of. Right? So that's 1 plus x. What's the next term here? This is where this starts getting trippy, okay? X squared over 2 factorial. I'm just going to write 2 times 1. All right? Look at how close those curves are from about here to here. Those look very, very similar, right? Let's add on my next term. X to the third over 3 factorial. Okay? This is starting to look like the same graph. And go out and go x to the fourth over 4 factorial. There's a factorial on here. I just haven't been going to it. It's over on the keyboard, over 4 factorial. Right? At numbers centered around this, around 0, you can hardly even tell the difference. And the more stuff that I put on here, the more terms, x to the 5th over 5 factorial. That's crazy, right? And this ends up looking very similar. So one of the purposes of these power series is that sometimes we can use them to approximate e to the x, like very close right here. And it's kind of just like the tail that's not matching up, you know? So that's something that we're going to get into, and I think you guys are really going to like it. Okay. Check this out. All right. This is a little proof that I'm going to show you of something that I think you guys will think is cool. All right. In example 1, this, remember, first term, and then it was minus negative, so that was r. So it's an alternating multiplies by t every time. It alternates, or you could say it multiplies by like negative t every time. Okay? Now, what we're going to do is we're going to integrate both sides of this. So I'm going to integrate that. I'm going to integrate that. Okay? And you guys should be able to recognize the integral of this. This is an ln problem. So it's ln of 1 plus t evaluated from x to 0. Okay, I'm just going to work on the left for a minute. When I go to do top minus bottom, I get ln of 1 plus x minus the ln of 1. And you guys know this, but the ln of 1 is 0. So I just get ln of 1 plus x. Okay? Now, on the other side, I'm going to integrate this, and I'm going to integrate it like term by term, okay? Okay, check it out. The integral of 1 is t. I'm doing it like to dt, and then I'll evaluate it. The integral of 1 is t. This next one is t squared over 2. Then it's plus t to the third over 3. Minus t to the fourth over 4. Now remember, okay, we have this term, which we're going to make that integral be t to the n plus 1 over n plus 1. All right, and when we do that, well, I'm actually not going to worry about putting the general term. It gets like kind of weird. I'm just going to go dot, dot, dot. Okay, evaluated from x to 0. Now when I plug x in, this becomes x minus x squared over 2 plus x third over 3 minus x to the fourth over 4. Okay, top minus bottom. And when I plug in 0, right, you just get 0 minus 0 plus 0 minus 0, dot, dot, dot. So those all just go to 0, okay? Okay, so now I came up with this equation here, all right, that the ln of 1 plus x can be approximated with that series, okay? Now, this is saying use the result of example 8 to write a power series for just ln of x. All right, this is ln of 1 plus x, so how am I going to change that around? Okay, got to be a little tricky here. Check it out. I'm going to substitute in, and I'm going to do the ln of 1 plus, and then I'm just going to make sure I write it the right way. X minus 1, because that equals the ln of x, because the 1's cancel out, okay? Now look, what that means is that everywhere I see an x, I'm actually going to substitute in an x minus 1. So substitute in x minus 1 wherever you see an x, okay? So now this becomes, in parentheses, x minus 1. And then x minus 1 squared over 2. X minus 1 third over 3. Minus x minus 1 4 over 4 plus, like that, okay? Now, again, let's kind of like take a look at this. So it's x minus 1. Now notice this one does not have factorials. The E one did. This doesn't have factorials. Okay, so let's go ahead and graph y equals, ln is right down here somewhere. There it is, ln of x. Okay, and the first term was x minus 1. All right, again, not a great comparison. The next term is x minus 1 squared over 2. That's not good at all. Oh, it's actually minus, isn't it? I forgot to put in my alternating. So there we go. X minus 1 squared over 2. Okay, that's not bad. That's not bad. That's getting closer to it, right? Plus x minus 1 to the third over 3. Pretty cool. Okay, that's looking pretty close right there. we'll just list one more right now, minus x minus 1 to the 4th over 4. Okay, and as you get, you know, if I get pretty closely zoomed in here, you can't really tell the difference between those two. Now again, we have to go out to a lot of terms, you know, to make it look like that. But that is a really good power series for the ln of x. All right, now if I'm writing this new series, this is just a question, something they ask you to do sometimes. X squared ln of x, right? So you say, okay, you go, the series ln of x is, put that on there. Well, we're always dealing with positive numbers, so we don't really need it. X minus 1 squared over 2, x minus 1/3 over 3, x minus 1/4 over 4. Okay, that means that x squared ln x is just x squared times each of these terms. And then that's x minus 1. Oh, I didn't write my x squared. Okay, and then it's x squared times x minus 1/3 over 3. That one was plus, and then this one is minus x squared x minus 1/4 over 4, dot, dot, dot. Okay? And that's it. And I think that's it for this lesson, right? Yeah. All right, so let's look at the homework that you guys should look at. Should really probably go up to at least number 23. And then after that, it's like kind of review, but it's still good review. I don't know, like all of this is really good review. Okay, but let's take a look at what you do on these things. Okay, so this first part, super important. So 4 terms, general term, sigma notation, interval of convergence. So all that stuff that we were doing, okay? Remember that you have to find the pattern A1 over 1 minus R. You have to identify what A1 is, and that's where you start, and what R is, and that's what you multiply by every time. This, we're kind of going backwards. So what you're going to do is list out all the terms and then put it into a function, A1 over 1 minus R. These are like all geometric. Okay? Then we had these power series for like e to the x, so that's just like a substitute in. There's x e to the x, that's multiplying the whole series by x, right? Some geometric power series over here, okay? And then this is interesting. So 14, 15, and 16 kind of go together. All right, we've got this. We substitute in x squared for everything, and then we can integrate it, and that helps me because the integral of 1 over 1 plus x squared is arctan, and so I can make this new series for arctan, okay? Anyway, so I'd like you guys to kind of go through there, and I'll write up my work as well, kind of at least try to go through like 23. All right, good luck.